Hi guys, and welcome to another episode of Chem Round, where we bring you the latest in chemistry. Today we're going to be talking about Pravastatin, but first let's take a look at what it's used for with Juliana.
Thanks guys. Today I'm going to talk to you about hypercholesterolemia. Cholesterol is a fatty, modified steroid which is insoluble in water. It can be taken in through the diet or synthesized in the body and is a precursor for many important steroid hormones. Cholesterol and proteins combine in the blood to form lipoproteins used for transport. There are two main types of lipoprotein: high-density lipoprotein, or HDL. This is known as good cholesterol. And low-density lipoprotein, or LDL, is known as bad cholesterol. Many factors can cause high cholesterol. A diet high in saturated fat can increase your bad cholesterol levels, as well as a lack of exercise, obesity, and regularly drinking large amounts of alcohol. A chemical in cigarettes called acrolein stops HDL transporting cholesterol from fatty deposits to the liver, leading to cholesterol building up in the arteries. Some underlying conditions such as diabetes can also cause high cholesterol, as well as several fixed factors such as age, gender, and a family history of hypercholesterolemia. As cholesterol is insoluble in water, when it accumulates in the wrong place, for example within the wall of an artery, it's hard to remove, eventually leading to an atherosclerotic plaque forming. These plaques can cause the artery to harden and narrow, restricting the blood flow and oxygen supply to vital organs such as the heart or brain. If left to get worse, these can lead to a number of serious conditions known as cardiovascular disease, or CVD. Types of CVD include coronary heart disease, peripheral arterial disease, stroke, and heart attack.
Thank you, Juliana. That was Pravastatin's use. And now back to the beginning with the discovery of Pravastatin. Over to Mariam and Hugo.
The discovery of Pravastatin. The search for a cholesterol synthesis inhibitor became an important aspect of research after a genetic connection between heart attack and cholesterol was made in 1939. Inspired by Fleming's success with molds, Akiro Endo, a Japanese microbiologist, discovered statins during his research on fermentation broth of penicillin citrinum. He found a natural product with a powerful inhibitory effect on the HMGR reductase enzyme. The active ingredient in the broth was known as citrinin, although it was later discovered to be toxic to the kidneys. There are other discoveries like compactin that were very effective but failed the animal testing stage of drug trials. Amongst many derivatives of compactin was pravastatin sodium. Its potency and tissue selectivity is one of the reasons it passed the drug trial. All obtained from A Historical Perspective on Discovery of Statins by Akiro Endo, Series B, page 484 to 493.
And that was Mariam and Hugo with the discovery of Pravastatin. Now we're going to look at the synthesis, structure and mechanism of action. Over to Fawad in the lab.
Oh, hi there. How do you see there? I'm going to talk to you about how we should go from this fungal molecule here to this plant structure. Let's have some fun. So let's talk about the synthesis of pravastatin. So pravastatin began from this fungal molecule here called penicillin citrinum, and this was fermented in the lab to give us compactin, also known as pravastatin. This was purified in the lab before sodium hydroxide was then reacted, and it is the ester from the lactone ring that breaks open to give us a salt on one end and alcohol on the next. So this undergoes a biotransformation step with the bacteria called Bacterium Streptomyces carbophilus, and this contains a cytochrome P450 enzyme that can selectively hydroxylate the C6 end of this structure to give us pravastatin.
Okay, so now we understand the synthesis of pravastatin, it's time to move on and talk about the structure of the drug. To begin, here is the structure of pravastatin. Working our way through the functional groups, we can see we have a beta hydroxyl group here, which will show polarity, an alpha ester functional group attached to the first cyclic ring. This group would be prone to hydrolysis within the body during metabolism and excretion of the drug. Two beta hydroxyl groups attached to the side chain here, and finally a carboxylic acid group at the end of the side chain, which is converted into a sodium salt when manufactured into the drug on the shelves, which we know as pravastatin sodium tablets.
Let's take a look at the mechanism of action. But first, let's see the synthesis of cholesterol. Cholesterol is made by reacting acetyl-CoA with acetyl-acetyl-CoA to make the cholesterol precursor HMG-CoA. Next, you use HMG-CoA to make mevalonate, isoprene units, squalene, and finally cholesterol. You use the reductive power of NADPH and the enzyme HMG-CoA reductase to make mevalonate. This is a rate-limiting step, and drugs are going to use this area to competitively inhibit HMG reductase so that mevalonate cannot be made, and consequently cholesterol. Here are the structures of the natural substrate HMG-CoA and pravastatin. As you can see, they are structurally similar. The hydrolyzed lactone ring on pravastatin mimics a tetrahedral intermediate produced by HMG reductase on HMG-CoA. This allows pravastatin to bind to the active site to a much greater affinity than its natural substrate. It is the bicyclic portion, as circled over there, that is going to bind to the coenzyme A portion of the active site and consequently cause reversible inhibition. Okay, let's take a look at the active site interactions. Pravastatin is going to change the conformational ability of the enzyme once it's binded to it. This allows it to have as many interactions as possible, and it causes a hydrophobic groove in the enzyme. This can accommodate pravastatin's hydrophobic groups, such as this over here, and lead to van der Waals forces. There are also going to be polar interactions taking place in the cis loop of the enzyme with amino acids such as serine and lysine, and also ionic interactions forming a salt bridge with the amino acids. There is also going to be hydrogen bonding with the hydroxyl groups on this molecule and pi-pi stacking. Example of a statin blocking the active site of the HMG-CoA reductase. Finally, it works by reversibly inhibiting HMG-CoA reductase, reducing cholesterol pools, and in the same way it has triglyceride lowering properties, this time by inhibiting hepatic synthesis of very low density lipoproteins. Pravastatin is one of the lower potency statins, but its increased hydrophilicity means minimal penetration through lipophilic membranes of peripheral cells and the blood-brain barrier. This means increased selectivity in hepatic tissues and fewer side effects when compared to simvastatin. It's also taken up by the liver by the active transport carrier systems, such as the independent sodium bile acid transporter. It's oral in active form with an absorption of 34% and a low bioavailability of 17%. Due to incomplete absorption in first part extraction in the liver. It reaches a peak plasma concentration at 1 to 1.5 hours.
So now we know the structure of pravastatin and how it's made and how it works inside the body. We're now going to look at side effects. Now over to Jenny.
Alright, thanks guys. Let's take a look at some side effects. So there are two types of effects, on-target side effects and off-target side effects. And now, we will look into more details of the on-target side effects of pravastatin first. These are the exaggerated NFS pharmacological effects at the target of interest. Like all the other statins, pravastatin competitively inhibits hepatic HMG-CoA reductase, an enzyme involved in cholesterol synthesis. It changes the hepatocellular lipid concentration and plasma membrane permeability, which may cause transaminase enzyme leak and therefore an associated inflammatory response giving rise to a biochemical hepatitis. It could also cause jaundice, which is a yellowing of the skin and whites of the eyes. This is one of the relevant consequences of liver dysfunction, so it is advised to be avoided by patients with liver disease. Moving on to the off-target side effects. They are the adverse effects as a result of modulation of the other targets. These may be related biologically or totally unrelated to the target of interest. Muscle effects is the main off-target side effects, which is most likely to be caused by the intake of pravastatin. Mitochondrial dysfunction is believed to be the main mechanism of statin-induced myopathy. It has been suggested that statins can play an antagonistic role on the conductance of chloride channels of muscular cells and reduce the flux through the cholesterol synthesis pathway. But they may also induce a chronic muscle contractile state, eventually leading to myopathy. It could also cause myositis, which you can see from the picture here. The patient could possibly develop inflammatory cell infiltration within skeletal muscles. This results in skin rashes on the face and the back of the hands. It appears to be a natural healing process, secondary to the muscular damage. In other words, the consequences of myopathy that we have just discussed on. Although in the overall, pravastatin is usually a well-tolerated drug, the experience of serious and fatal side effects is rare. A more conclusive solution is to remove the additional cholesterol being put into the body by managing diet and exercising. As such, a safe, healthy level of cholesterol can be maintained very effectively.
Thanks for watching.
This has been Rebecca.
This has been Mariam reporting for ChemRound.